My name is Edward Gao, and today I will be talking about the phenomena known as the ozone hole and its causes and effects. So, what is ozone? Ozone is a gas made up of three oxygen atoms, and it's signified by O3. It occurs naturally in small amounts in the upper atmosphere, or the stratosphere. It protects life on Earth from sun's ultraviolet radiation. In the troposphere, however, near the Earth's surface, ozone is created by chemical reactions between pollutants from vehicle exhaust, gas vapors, and other emissions. At ground level, high concentrations of ozone are toxic to people and plants. Before we dig deeper into a further discussion about ozone, we first need to understand the mechanism by which it is created. As we can see, the Chapman mechanism details the process of ozone production and decomposition. Note that we actually want ozone to be produced within the stratosphere, as it protects us from the UV radiation. Now that we understand a little bit more about what ozone is, what actually is the ozone hole? It was first discovered by the British Antarctic Survey from data obtained with a ground-based instrument from a measuring station at Halley Bay, Antarctica in the 1980s. The ozone hole is formed each year in the southern hemisphere spring, which occurs around September to November, when there is a sharp decline in the total ozone over most of Antarctica. During the cold and dark Antarctic winter, stratospheric ice clouds form when temperatures drop below -78 degrees Celsius. These clouds are responsible for chemical changes that promote production of active chlorine and bromine. When sunlight returns to the Antarctic in the spring, chlorine and bromine activation leads to rapid ozone loss, which then results in the Antarctic ozone hole. Although some ozone depletion also occurs in the Arctic during the northern hemisphere spring, wintertime temperatures in the Arctic stratosphere are not persistently low for as many weeks, which results in less ozone depletion. Anthropogenic sources of chlorine rose greatly with the release of CFCs, or chlorofluorocarbons, into the atmospheres. CFCs are man-made chemicals typically used in refrigerants. This exacerbates ozone depletion through what is known as a chlorine-catalyzed reaction. Here, we see chlorine derivatives bonding with ozone to ultimately result in a net loss of ozone that turns into oxygen gas. From this figure, we can see the growing CFC concentrations throughout the 1900s at various sites around the world. In general, as a concentration of CFCs increase, the amount of ozone depletion increases as well. This, combined with the natural effect of chlorine produced in the Antarctic, is what really creates problems in the ozone hole. This is a graphical depiction of what the ozone hole looks like. In the year 2006, not only was the hole the largest in surface area, but it also suffered the most mass deficit, meaning that there was less ozone over the Antarctic than ever previously measured. The scale used to measure the ozone levels is called the Dobson units, or DU for short. Essentially, one Dobson unit is equal to the number of ozone molecules needed to create a pure layer of ozone 0.01 millimeters thick at standard temperatures and pressures. Here we observe that the ozone layer is only 150 Dobson units at its thinnest, which is much lower than the global average of around 300. Not only does the ozone hole appear every year, but it's also growing in size. Here we can see that from 1981 to 1991, that the area where the ozone is thinnest, which is in red, has increased by several times its original size. A thinner ozone implies more heat and UV radiation striking the Earth, spelling harmful effects for flora and fauna. To combat the growing hole, what was known as the Montreal Protocol was enacted. The Montreal Protocol is an international treaty designed to protect the ozone layer by phasing out the production of numerous substances that are responsible for ozone depletion. In particular, it successfully phased out most CFCs emitted to the atmosphere. From this plot, on average, after the Montreal Protocol was enacted, we see that the size of the ozone hole stops increasing, and in fact appears to be on a downward trend. However, CFCs have a long lifetime, around a magnitude of 50 to 100 years, so it will take a long time before the ozone hole returns to its original size. But the Montreal Protocol is a great example of a global effort to reduce harmful emissions, and we should learn from these lessons going on into the future.